Let us start the lecture. Today I will do the second method of designing IIR filters. In the previous lecture, we started with the IIR filter design using approximation of derivatives. So in the approximation of derivatives, we saw that how the differential equations which can be used to describe an analog system, and from those differential equations how we can use the backward Euler's approximation to convert the differential equations to difference equations, right? And then we can apply the method of approximation of derivatives and the transformation to convert an existing analog filter to a digital filter. We used one transformation, and in which we saw that the mapping of the S-plane, that means the left-hand side of the imaginary axis of the S-plane goes into the circle with radius z equal to 1/2 and center also at z equal to 1/2. Approximation of derivatives method is useful for low frequency, that means for the low pass filter design or band pass filter design, in which the resonant frequency, in which the smaller resonant frequencies are there. But the approximation of derivatives is not a very good choice for the high pass filter design. But we applied some complex transformations, and by applying those complex transformations, the left-hand side of the imaginary axis can be mapped to unit circle, right? But that will lead to increase in the complexity of the system. That we saw with an example also, where the analog filter had 2 poles, but when we converted it into a digital filter, the system resulted into having 4 poles. So that means the complexity of the system will increase if you apply the complex transformations, right, in the case of approximation of derivatives. But let us study one second method of IIR filter design, and the method is known as the impulse invariant method of impulse invariant method. Now, in transforming an analog filter to digital filter, we must obtain either Hz or Hzen from the analog filter design. In such transformation, we generally require the essential properties of the analog frequency response be preserved in the frequency response of the resulting digital filter. That is quite obvious. That is the requirement. This implies that we want the imaginary axis of the S-plane to map into the unit circle of the Z-plane. A second condition is that a stable analog filter should be transformed to a stable digital filter. That is also the requirement of designing IIR digital filters. Now let us look at what is the impulse invariant method. Now in this method, we start from an analog filter of impulse response HAT. So HAT is the impulse response of the analog filter, and the system function has system function is HAS. That is the usual practice we are dealing with designing the analog filters to digital filter. Now the objective of our design is to realize an IIR filter with an impulse response HN, which satisfies. Of course, we have HAT available. How can we get HN from HAT? Just replace T with NT. That is the sampling process. Now the characteristic property preserved by this transformation is that the impulse response of the resulting digital filter is a sampled version of the impulse response of the analog filter. Now this is HAT is the impulse response of the analog filter and HN will be the impulse response, the sampled version of the impulse response of the analog filter, right? So that we know. So this is the diagrammatic explanation of that. We have already seen these things, but let's once again see. Let's say this is the HAT, the impulse response of some filter, right? And HA omega capital omega is the frequency response of this analog impulse response once we take the Fourier transform in the continuous domain, right? Corresponding, when we sample this HAT, we get HN. So this is the sampled version of the HAT, which we call as HN, and this is H omega, which is the digital spectrum of the. This is the frequency response in the digital domain, and we know that the the spectrum will repeat. If you see this spectrum, this digital spectrum is exactly the replica of the analog spectrum from -pi to pi, but it will repeat with a period of 2 pi. That we already know that once we convert the impulse response in the continuous domain to the digital domain, then the digital spectrum will repeat with a period of 2 pi. So that's what that is exactly what this diagram tells, right? Now the important thing in the impulse invariant method is that there can be present aliasing, because we know that the digital spectrum repeats, but there can be the presence of aliasing. That means the digital spectrum, the nearby digital spectrum, the consecutive digital spectrum may interfere with each other, resulting into folding frequency and all that. We have already discussed those things. Aliasing problem is there, right? Now, how can we avoid aliasing? The aliasing problem can be avoided if we select the sampling frequency, if we select a higher sampling frequency. If we select very high sampling frequency, the aliasing problem can be avoided, right? The sampling frequency affects the frequency response of the impulse invariant discrete filter, because this is the response of the analog filter, this is the impulse response of the digital filter, this is the frequency response of analog filter, and this is the frequency response of the digital filter. Now the sampling frequency, as I was saying, will affect the characteristics of the resulting digital filter, because the smaller sampling frequency may lead to aliasing problem in the impulse invariant method. A sufficient high sampling frequency is necessary for the frequency response to be close to that of the equivalent analog filter. Thus, due to aliasing, the frequency response of the digital filter will not be identical to that of the analog filter. So how do we find the filter coefficients of the IIR filter in this design method? Now, what is the procedure of this is the problem that I discussed in the impulse invariant method. The problem is that there can be aliasing present in the impulse invariant method, but the choice of sampling frequency will of course give us a remedy towards the aliasing, but still aliasing problem is there in impulse invariant method. But what is the procedure of designing? The procedure says we are given the system transfer function in the analog domain, HAS. Usually you will be given with this type of system function in the S domain, which explains the analog filter. What we will do is we will first take the inverse Laplace transform and we will convert it into the impulse response in the time domain. Okay, HAT e to the power minus bt. So this is the, once we take the inverse Laplace transform, we'll get HAT equal to e to the power minus bt. Now from here, what we will do, we will take the sampled version. How we get the sampled version? We will replace t with n capital T. So this small t will be replaced with n capital T. So HANT is equal to e to the power minus b n capital T. So HANT can be usually written as HN. So this is given by e to the power minus b n t when n is greater than or equal to 0, and 0 when n is less than 0. Now for this, if we take the Z transform of this Hn, Z transform will be given by Hz equal to 1 over 1 minus e to the power minus bt, because this, and this is the the coefficient will be e to the power minus bt, Z to the power minus 1. So this is the transfer function Now, what we have done in this slide, you are given with a filter with system function 1 over s plus b. We have to get the digital equivalent of this. How do we get? We take the inverse transform, we convert it into impulse response in the time domain, that is the analog impulse response. Then we sample it, right, by replacing small t with the n capital T, right, and then we take the Z transform and we get the transfer function of the digital filter, and this is the coefficient of the e to the power minus b capital T is the coefficient of the filter. All right, so that's the procedure that we will be using. Now, what is the transformation? The transformation will be, right, we start from 1 over s plus b. What is the equivalent digital filter? 1 over 1 minus e to the power minus b capital T z to the power minus 1. We will use it as a formula, we will take it as a transformation, that 1 over s plus b will be equivalent to 1 over 1 minus e to the power minus b capital T z to the power minus 1. And we have seen the procedure. How did we get it? Right. Now it is seen that hz is obtained from HAS by using the mapping relationship 1 over s plus b. We get hz, which is the digital filter, from HAS, which is the analog filter, by using the mapping relationship 1 over s plus b to 1 over 1 minus e to the power minus b capital T z to the power minus 1, b greater than 0, where t is the sampling period. Now let us try to understand the problem in the impulse invariant method. So this graph, which is the S plane, right? S plane, if we the x-axis of the S plane is sigma, the y-axis is j capital omega, which is the analog explanation of the S plane, analog frequency domain, analog frequency in the S plane. Now, in the impulse invariant method, if you start putting the values, the strip, the left hand side, we divide the left plane of the complete S plane into strips. Now, what are these strips? The strip will go from minus pi to pi by t, minus pi by t to pi by t, right? Minus 3 pi by t to minus pi by t, pi by t to 3 pi by t. So let us look at this strip going from minus pi by t to plus pi by t. So what happens with this technique is that this strip only from minus pi by capital T to plus pi by capital T will go in with this mapping. With the, if you substitute the values of S and you get the values of inside the unit circle, what you will get is that this strip from minus pi by capital T to plus pi by capital T will go inside the unit circle. Complete, it will occupy the complete unit circle. All right, so that's the meaning, the mapping. Now the next strip, that means from pi by capital T to 3 pi by capital T, will also occupy the same unit circle space. This strip from minus 3 pi by capital T to minus pi by capital T will occupy the same same unit circle space, and so on. And that means all these strips within this frequency range will go inside the unit circle. So that's what is said. Each strip maps onto the interior of the unit circle. All right, which basically explains the aliasing problem. That means the higher frequencies are going inside, because we saw here that the impulse invariant method has got the problem of aliasing. So that is what another explanation of the mapping of the S plane to the Z plane. This happens in the impulse invariant method. Impulse invariant method is inherently suffering from the problem of aliasing. Now, the j omega axis is mapped. This has to be actually one. Let me put this. This has to be. wait, let me correct here only because then it will be left as it is. Okay, so that's what is the thing. That means the j omega axis, this is the j omega axis, right, is mapped into the unit circle of that plane as shown in the previous slide. However, this mapping is not one-to-one. What is one-to-one mapping? That the complete j omega axis, not divided into strips, the complete space occupied on the left side of the j omega axis must map into the inside of the unit circle. But what is happening here? The strips from minus pi by capital T to plus pi by capital T is being mapped to inside of the unit circle, and pi by capital T to 3 pi by capital T is also being mapped to the unit circle. So this is not one-to-one mapping. This is many-to-one mapping. However, this mapping is not one-to-one. Since omega, which is the digital frequency, is unique over the range minus pi will start from here and it will end at pi. So minus pi to pi, it is unique in this range. That's what is said. The mapping, that means this digital frequency equivalent, this small omega is the digital frequency, capital omega is the analog frequency. This is the relationship. Now this from this expression, we can find out that when capital omega is minus pi by capital T, so you put the value of capital omega here, minus pi by capital T. What is small omega? Minus pi. And when you put capital omega to be pi by capital T, you will get small omega to be pi. So that means minus pi to pi, the mapping implies that the interval, this interval maps into the corresponding values of minus pi to pi. Furthermore, the frequency interval pi by T to 3 pi by T also maps into the interval minus pi to pi. And in general, so the interval 2k minus 1 pi by T to 2k plus 1 pi by T goes into this digital frequency range minus pi to pi. Thus, the mapping from the analog frequency omega, capital omega, to the frequency variable small omega in the digital domain is many to one, right? Which simply reflects the effects of aliasing due to sampling. Because what we are doing here is that we are doing the sampling and there will be the problem of aliasing. Of course, sampling, the aliasing problem can be reduced by a suitable choice of the sampling frequency. Correct? So this is the method of impulse invariant method of converting an analog filter to the digital filter. And I have also explained you the problem of the impulse invariant method. The impulse invariant method suffers from the problem of aliasing. Okay. This is the same explanation that strip from minus pi by T to pi by T goes inside the unit circle. The same explanation, right? Diagram. This diagram is given in ProCase, so I put this diagram here so that once you find it in the book, you should not be surprised. Now, let us take an example of converting an analog filter to a digital filter using the impulse invariant method. Now, HS, which is the system function of the analog filter, let's say this analog filter is 2 by s plus 1, s plus 3. Now, by using the partial fraction, I can convert it into 1 over s plus 1 minus 1 over s plus 3. And using the same transformation, which transformation? This transformation, 1 over s plus b in the analog domain goes into 1 over 1 minus e to the power minus b capital T z to the power minus 1 in the digital domain. Using the same transformation, I can convert 1 over s plus 1 minus 1 over s plus 3 to this. Now b in this case, as it is b is 1, in this case b is 3, so I can get hz from here 1 over 1 minus t, and this is the second term. And I can solve the second term. The denominator polynomial will be second order polynomial z to the power -2, and there will be 0 also with this coefficient e to the power minus capital T minus e to the power -3 capital T. This is the coefficient, right? And two poles will be there. These are the coefficients of the filter, right? This is the conversion. What we have done in this example, where we have converted an analog filter to a digital filter using the impulse invariant method. What is the impulse invariant method? 1 over s plus b gives me 1 over 1 minus e to the power minus b capital D z to the power minus. This is the transformation of converting the analog filter to the digital filter using the impulse invariant method. And I have already explained you the problem in the impulse invariant method. The impulse invariant method suffers from the problem of aliasing. Okay. Now let us look at one more example. Use the impulse invariant method to design digital filter from an analog prototype that has a system function. So this is the system function given, right? To design a filter using the impulse invariant method, expand HS in a partial fraction form. So we will have to put it in a form from where we can transform it into digital domain. We take the partial fractions, we solve it using the partial fractions. The partial fractions will give me this half s plus this, half s plus this. These are the roots that I will get. All right. So I can express this as 1 over. So this expression takes the form of 1 over s plus b, where b is equal to a plus jb, and here that means this has taken the form from where I can use the impulse invariant transformation to convert it into a digital filter. So I use this 1 over s plus c, this impulse invariant method, and once I solve this, so this will be my coefficient. A plus jb will be my first factor here, e to the power minus a plus jb, and e to the power minus of a minus jb. Right. So I can apply this transformation to solve, and further if I solve this numerator and the denominator polynomials, I will be able to get this filter, which is HZ filter, having 1 minus e to the power minus a capital T cos of b. This is the coefficient, right? And these are two other coefficients of the denominator polynomial. This coefficient is for the numerator polynomial, and these are the coefficients of the denominator polynomial. So this is the IIR filter design, digital equivalent of the IIR filter. Which filter? This filter, s plus a whole square plus b square. So this is the way how you will be using the impulse invariant method to convert an analog filter to a digital filter. All right. So this we can say, so this is the filter we obtained. Now we can compare the general form. Now this HZ can be written as 1 plus a1 z to the power minus 1 plus b1. So these are the coefficients. I mean, this is the same thing. How this is the filter only. So HZ is the filter. Okay. Now let us take one more example. This we know, we are familiar with this type of filter. This is a second order Butterworth filter, right? HS is where HS is given by 1 over s square plus under root 2s plus 1. Assume that the 3 dB cutoff frequency is 150 Hertz and the sampling frequency is 1.2 kilohertz, 1.28 kilohertz. So if you remember, this is a Butterworth polynomial is a normalized polynomial, because here 1 comes. So how to denormalize it? We have to how to denormalize it? If we try to calculate the gain of this filter, if we try to, actually there are 2-3 more things which are being done here. First thing, let me explain you one by one, right? So we are designing the impulse invariant method, and this is the filter given. This is the second order filter given, Butterworth filter. It's an all pole filter, right? It's a low pass filter with this, it's a second order filter prototype. Okay. So assume that the 3 dB cutoff frequency of the digital filter, that means this is the cutoff frequency, which is 150 Hertz, and the sampling frequency is 1.28 kilohertz. This is given. We have to design a digital filter to approximate the following normalized transfer function. We have to use this transfer function to normalize it. I mean, this is a normalized transfer function and we have to use this. Okay. Now, what is h of omega? Actually, if you take the hz from here, right? So you will be able to get hz from here. Actually, the solution is not complete. Okay, some solution is missing. So this is my hz. How you will get this hz? You will get this hz by this is hs. Once you do the partial fractions, right? You will be able to obtain the ht out of here. So, and if you use the impulse invariant transformation like this 1 over s plus b, the transformation is 1 over 1 minus e to the power minus ct z to the power minus. Once you do that, the solution is not this solution is not complete. But anyway, so you will be able to get hz here, the new transfer function. All right, and how to, you know that this is the normalized transfer function. How to denormalize the transfer function? If you remember, in my previous lectures, I told you that how to do the denormalized transfer function. Replace every s with s by omega c. Right? What is omega c here? This is 150 Hertz. This will be, you can calculate omega c from here. 2 pi f will be your omega c. So you replace every s with s by omega c. So whatever the transfer function you will get, that will be the denormalized transfer function. Once you get the denormalized transfer function, you can use the impulse invariant method to get hz. So this is hz you will get. Now from here, what happens is that you can also find out the DC gain of the system. How you will be able to find the DC gain of the system? You replace every z with e to the power j omega. So once you replace every z with e to the power j omega, and then you put omega equal to 0, what you will get is that you will get the DC gain. So that is what is calculated here. In this system, you get the DC gain, right? Once you replace z with e to the power j omega, and once you do j omega, once you put omega equal to 0, DC gain will come out to be 1223. So it's a very large gain. To keep the gain down and to avoid overflows when the filter is implemented, it's common practice to divide the gain by fs. So this gain is divided by fs. What is fs here? Fs is 1.28 kilohertz. So the gain, when the gain is, that's what is said here, when the gain, it is common practice to divide the gain by fs. Thus the new transfer function becomes this. So let me explain actually what we have done here in this example. Actually the solution is not complete. I have left the solution to be completed by you people. Now let me explain the problem. What is this example? In this example, you are given hs, right? And we know that from our background, we know that this is a Butterworth filter, low pass filter prototype. This is a normalized Butterworth filter. We need to denormalize it. How you will denormalize it? Right? Once you have to apply the impulse invariant method, you will have to denormalize it. How to denormalize it? Replace every s with s by capital omega c. From where you will get capital omega c? You are given with fc, which is 150 Hertz. 2 pi into 150 will give you capital omega c. So you replace every s with s by 2 pi this fc. So you will get the denormalized analog system function. You take the partial fractions and you obtain the ht. You obtain the you do the partial fraction, you do the inverse Laplace transform like we did here, right? Let me show you. This was the transfer function given. So you took the partial fractions, you then took the inverse Laplace transform, and you obtained this expression. So that's what exactly you are supposed to do here. You are given with a normalized transfer function. You will have to denormalize it by replacing every s with s by omega c, and then use the partial fractions, use the impulse invariant transformation to obtain the digital filter. All right, but in this expression, that is an additional thing you are being told here. What is the additional thing? Now this system, any system can have a large DC gain. Now what is the DC gain? DC gain can be calculated when you get the Z transform, right? You replace Z with e to the power j omega. What is DC? DC value is when small omega equal to 0. So when small omega is equal to 0, right? And you in the expression for h omega, you put omega equal to 0. Once you obtain hz, replace every z with e to the power j omega, and then you substitute the value of omega equal to 0. Then what the answer you get is the DC gain of the system. Now some systems may have very high DC gain, as is here in this example. Such a large gain is characteristic of impulse invariant. Normally, using the impulse invariant method, the filters that you will get are of very large DC gain, which is not every time expected, because unnecessarily raising the DC gain of the system may lead to design of the other electronics involved and may lead to a difficulty in the design of other electronics. So you will have to bring down this gain. How you can bring down this gain? To keep the gain down and to avoid overflows when the filter is implemented, it is common practice to divide the gain by Fs. Now we divide this, gain is given to be 1223, Fs is given to be 1.28 kilohertz. So we divide this high gain with Fs value. Once we divide that, we get this transfer function. So this transfer function is a new transfer function with a small value of DC gain, or you can also say that normalized DC gain. That means this transfer function has very small value of DC gain, and then you can use this transfer function to design your filter. So that is an additional problem handled in the design of the filter. Otherwise, the impulse invariant method, that's the structure we have obtained from where? From this HZ system function. So we can draw the structure also. So in the crux of the matter is, this is HT given, we sample it. The problem in the impulse invariant method is that the sampling frequency affects the frequency response of the digital filter obtained using impulse invariant method, and there is the problem of aliasing. This has to be understood. A sufficient high sample frequency is necessary for the frequency response to be close to that of the equivalent analog filter. Low degree of aliasing can be achieved by making the sampling frequency high. So it all ultimately then comes to the selection of the sampling frequency. So once the sampling frequency is selected high, the aliasing problem will be reduced. But inherently, the method of impulse invariant method suffers from the problem of aliasing. Now, how to avoid aliasing problem in the design of IIR filters using impulse invariant method. The technique to avoid aliasing in the design of IIR filters using the impulse invariant method, the technique is known as bilinear transformation. This is by far the best technique to design IIR filters, right? And it will avoid the problem of aliasing. But in bilinear transformation, another problem results, which is the frequency warping problem that we will see. What is the problem here? The bilinear transformation yields stable digital filters from stable analog filters. The impulse invariant technique may not, because of the aliasing problem. Also, the bilinear transformation avoids the problem of aliasing encountered with the use of impulse invariant transformation, because it maps the entire. Now, what is the difference between the bilinear transformation and the impulse invariant? If you see if you remember what happened in the impulse invariant method, these strips from minus pi by capital T to pi by capital T, this strip will go inside the unit circle. Pi by capital T to 3 pi by capital T, this strip will go into the unit circle. That means these frequencies will go inside the unit circle, leading to aliasing problem. But what happens in the bilinear transformation, right? So that is to be understood. What happens in the bilinear transformation, the complete left side of the J capital omega axis, this complete left side of the S plane goes inside the unit circle. That means in the bilinear transformation, there is one-to-one mapping of the complete left side of the S plane to the inside of the unit circle. There is a one-to-one mapping here in the bilinear transformation. Therefore, bilinear transformation avoids the problem of aliasing. That is to be understood clearly. But it results into the frequency squeezing. That is also known as frequency warping. I will come to that. But you must understand how the bilinear transformation avoids the problem of aliasing. That means the complete left side of the j omega axis goes inside the unit circle and right side goes outside the unit circle. Image of the left hand S plane. Okay. Now, so this was the explanation for the impulse invariant method, where the strips go into, each strip maps into the interior of the unit circle. But in the bilinear transformation, that's the difference. So these two slides actually explains the difference between the mappings of the bilinear transformation. This is bilinear transformation. This is impulse invariant method. In this kind of mapping, okay. Now, let us look at what is this. What is the bilinear transformation mapping? In the impulse, this mapping 1 over S plus B in the analog domain transformed into 1 over 1 minus e to the power minus b capital T z to the power minus 1 this is the mapping. This is the transformation in the impulse invariant method. Now let us look at the bilinear transformation. What is the bilinear? How can we transform an analog filter to a digital filter? What is the transformation that we will apply? Now this is a general expression, z equal to e to the power s capital T. This is the general expression. This is the general relationship between the z transform and the Laplace transform. You can say s is there in the Laplace transform, z is there in the z is the z transform. This is the normal relationship between z and s. This is how they are related. Now how we will use this, z equal to s e to the power s capital T. Sigma, okay, I'm not coming to sigma at present. So z is equal to e to the power s capital T. This is the relationship between the Z transform and the Laplace transform. Now I can write this e to the power s capital T as e to the power s capital T by 2 divided by e to the power minus st by 2. I can write like this. I can expand the numerator portion and the denominator portion using the power series. I can expand it into 1 over 1 plus s by capital 1 by 1 plus s capital T by 2 and so on. I can expand the denominator expression also. If I drop the higher order terms, what I am left with, z equal to 1 plus s capital T by 2, 1 minus s capital T by 2. Now, if from here I calculate the value of s, therefore s is equal to 2 by capital T, 1 minus z to the power minus 1 divided by 1 plus z to the power minus 1. This is the bilinear transformation. Every s in the analog filter has to be replaced with this factor to get the digital filter out of the analog filter. Every s has to be replaced with this. This is known as bilinear transformation. This is the transformation of the impulse invariant method. The problems also I have explained. This is the bilinear transformation. S is equal to 2 by t, 1 minus z to the power minus 1 divided by 1 plus z to the power minus 1. Now, the aliasing is avoided definitely because the complete j omega axis will be mapped inside the unit circle. The price paid for the avoidance of aliasing is an introduction of the distortion in the frequency axis. And it is very obvious, this is a strip going inside the unit circle. Here, in the case of bilinear transform, the complete j omega axis goes into the unit circle. So there will be distortion in the frequency axis because this is a large portion being mapped inside the unit circle. So that's what is said. The price paid for the avoidance of aliasing is an introduction of distortion in the frequency axis. Consequently, the design of digital filters using the bilinear transformation is only useful when the distortion can be compensated. Whatever the distortion in the frequency axis results, if we can compensate that distortion, then bilinear transformation by far is the best choice for design of digital IIR filter. And we can do that. We will see that how to compensate for the frequency axis distortion. All right, let us look at one example. First of all, we have a system function HAS, right? Such that, and this is the analog transfer function given to us. HAS is B over S plus B. Had it been the impulse invariant method, we would have applied 1 over S plus B transformation equal to 1 over 1 minus e to the power minus B capital T z to the power minus. But here in the bilinear transformation, as I told you, what you need to do is you need to replace every s with this value. So that's the bilinear transformation. So in this expression, every s has to be replaced with 2 by capital T, 1 minus z to the power minus 1, 1 plus z to the power. That's what we do here. So we obtain hz by b over, we replace this s with this factor, right? And we get this digital filter out of it using bilinear transformation. All right. Now let us try to understand the problem of frequency distortion from this example only by choosing the values of b to be 1000 and capital T to be 1 by 1000. To simplify this expression and to plot it, let us try to look at what happens with the frequency axis. Okay. Now we first of all obtain the frequency response. How to obtain the frequency response? In the analog domain, take the Fourier transform, that's one method, or replace S with J capital omega. So once you replace S with J capital omega, you will get, this is the frequency response in the analog domain. All right, we plot the frequency response in the analog domain, the magnitude response. Right, and along the x-axis is capital omega, along the y-axis is magnitude response, right? And we obtain the graph like this. But once we go to the digital domain, right, we replace z here with e to the power j omega. Once we do that, let me see some. I'm finishing. I'm finishing. Okay, because I will not be able to complete the bilinear transformation. Okay, let me finish here, because let me start tomorrow fresh on bilinear transformation, so that the things can be picked up from here only and explained in a nice way. And I will also briefly discuss about impulse invariant method again, so that the correlation can be established with the bilinear transformation, and how aliasing is avoided, and how the two techniques are related to each other. So I finish my lecture here. Tomorrow I will be completing with the bilinear transformation, and we will take more examples. Thank you so much for joining. Thank you. Today the attendance is very less. Only 67 people came. I don't know. I would request the people, the CRs of the class, to inform the people to attend classes, because once some kind of examination happens, this is a difficult subject. Let me tell you, this is not because once the syllabus will pile up, you will find it difficult to grasp the things all together. So you will have to go with the syllabus day by day, But anyway, thank you so much for joining. Thank you.